We've completed a review of continuity and in behavior and limits. And then we come to an interesting little problem right at the end of this chapter section. This is a physics problem. Um, and let's just read through it because we're going to have to think about this a little bit, but maybe not too hard. It says that dynamic pressure is the pressure generated by the velocity of a moving fluid and is given by this formula, Q of V. Q of V is going to be dynamic pressure. So Q of V is dynamic pressure. And that's equal to the density, which is designated. This looks like a P, but actually in the physics world, this is the lowercase Greek letter rho, is the density of the fluid, and V squared, is the velocity of the fluid. And then we're asked this question: what would happen to the dynamic pressure, Q of V, of a fluid if the velocity were to continuously increase? So now we got this formula though. Q of V is equal to rho times velocity squared, or density times the velocity squared over 2. And you might be thinking, well, I really don't know. But let's think about this for a moment. We got a fluid, a given fluid, and it's got a density. We don't know what that density is. But in this formula, we can assume then that it is a constant. And so we really could just assign a value to that rho, and I don't know, how about 1? So what if we just said that the density is 1, and I don't know if it's 1 or 100 or a half or 0.0004 or what it is. But I'm just going to make an assumption that it is 1, and now I got V squared over 2. And maybe I just want to do a table of values right quick. I got X and Y. So what if the velocity, I don't know, what if the velocity is 1? V, X being the velocity, substitute that. Well, 1 squared divided by 2 is 1/2. Well, what if the velocity is 2? Well, 1 times 2 squared, 4 over 2 is 2. And what if velocity is 3? Well, 1 times 3 squared is 9. 1 times 9 is 9 divided by 2. That's going to be 4.5. And we can see that the dynamic pressure, Q of V, is going on out to infinity. And so the dynamic of pressure would then appear to be approaching infinity. Let's just look at it on a calculator just for a moment. Now, I kind of reasoned our way through that formula. Rho times velocity squared over 2 equals the dynamic pressure, or density times the velocity squared over 2 equals the dynamic pressure. But let's see, what if I go in here and I just calculate? Now, remember, we assumed that rho, the dynamic pressure, was a constant, and we just assigned it a value of 1. What if I assigned it a value of 2, just for fun? And instead of V for velocity, I'm going to use X squared. And then we're going to divide by 2. Now, I'm going to go into my window before I look at my graph, because I'm thinking here again, okay, velocity. Well, velocity is probably not going to be negative if it's a scalar quantity. Remember, we're talking about physics. But if it was displacement, if it were, what's the right word? Gosh, it's just escaping me right now. Maybe I'll think of it as we go along. Maybe it's vector, yeah. That could be negative. But I'm just going to set my X minimum at 0, because I'm just going to look at positive values. X going in a positive direction, velocity being positive. And I'm going to go in here and take a look at my graph, and boom, there it goes. What else is my one to show here? Okay, that's good. All right. And then if I go to my table right quick, second graph, and start scrolling down here in a positive direction, well, we did 2x squared, so when x is 1, y is 1. When x is 2, y is 4. And as I keep scrolling and more positive x's, I can see that y is getting larger and larger. And even when x is 20, y, or the dynamic pressure in our case, is now 400. And it's just additional proof that as the velocity increases, the dynamic pressure is approaching infinity.